Hello everyone, welcome back to my channel Ankara Education. Our today's topic is types of semiconductors. Before going into our topic, let us define semiconductor first. A semiconductor is a device whose conductivity lies between the conductors and the insulators. This we have discussed in our earlier sessions. Examples of semiconductors are silicon, germanium and gallium arsenide and so on. There are so many examples, but we are taking only some of them. First of all, let us draw the silicon structure first. Silicon, its atomic number is 14, so it can be drawn like this. Silicon, let us consider the silicon atom. If there are 4 such silicon atoms, they are bounded like this structure. This structure is called as lattice. Means each silicon atom here has 4 valence electrons, 1, 2, 3, 4. These 4 valence electrons are shared further by 4 atoms, 4 silicon atoms again. This structure forms the covalent bondings between the 2 atoms. Means there exists a covalent bond between all the 4 silicon atoms present. To the thermal energy, the free electron, there is a formation of free electron, means the thermal energy breaks this covalent bond and this electron is now free to move anywhere within this structure. That means it can be combined with anyone until it collides with some atom again. This absence of electron in this covalent bond will form a hole. This is how a hole is formed in the lattice of this bond in silicon atom. The energy required to break different covalent bonds is different. So, at a time, at room temperature, all the covalent bonds are not broken to create innumerable free electrons. The energy Eg required for germanium to break the covalent bond is 0.72 electron volts, whereas the energy required to break the covalent bond for silicon is 1.1 electron volt for silicon at room temperature. This has to be remembered, at room temperature. When a bond is incomplete so that a hole exists, it is relatively very easy for a valence electron in a neighboring atom to leave its covalent bond and to fill this hole. An electron moving from a bond to fill a hole leaves a hole in its initial position. Means if suppose this electron is moving to the position of this hole, then it leaves a hole in this position. Means the movement of electron from its original position to the new position creates a hole in the previous position. Here we can observe that only the electrons are exchanging their position and thereby current is flowing. In other words, the current is due to the holes moving in the opposite direction to that of electrons. To explain this, let us consider one example. In a row, say there are 10 ions, 1 to 10. Except for 6, all the covalent bonds of the ions are intact. The ion 6 has a covalent bond broken. Means there is a valence electron going away from the 6th position. So there is a vacancy here. Now imagine that an electron from ion 7 moves into the hole at ion 6. That means the electron here, it moves to the 6th position. Then it leaves a hole in the 7th position and fills up the hole at the 6th position. That means the electrons are moving from one position to another position. Thereby they are creating holes in the new position. So we can say that the movement of holes is opposite to the direction of movement of electrons, is opposite to the direction of electrons. Thereby the current flows and the holes behaves like positive charge equal in magnitude to the electron charge. In a pure semiconductor, the number of holes is equal to the number of electrons. Number of holes is equal to the number of holes for a pure semiconductor. I can say this concept is analogous to passengers traveling in a bus. In a bus is the semiconducting material, say. Standing passengers are the free electrons. When a sitting passenger gets down, a hole is created. This hole is filled by a free electron, that is standing passenger. This process goes on as the bus is moving from stage to stage. This is analogous to our case. If there are many standing passengers without any vacant seat, it is analogous to N-type semiconductor. And if there are many seats vacant without any standing passenger, it is like a P-type semiconductor. This we will discuss in our next discussion. Semiconductors are classified into two types. One is the intrinsic semiconductor and other one is the extrinsic semiconductors. First, let us discuss about the intrinsic semiconductors. Intrinsic semiconductors are the pure semiconductors, means there are no impurities added to the semiconductors. For example, see this structure, above structure discussed. That means here this is a pure semiconductor because all the atoms here are silicon. There are no other atoms involved here. So this is an example of intrinsic semiconductor. And the free electrons are only due to the natural causes. That means like temperature, increase in temperature, thermal agitations, etc. In extrinsic semiconductors, we have again two types. One is the P-type semiconductor and other one is the N-type semiconductor. These are different because the impurities added are different from each other. Let us discuss about the extrinsic semiconductor with an example. Here, apart from silicon, there is one impurity called as arsenic. This is from fifth group. So, for an intrinsic semiconductor, if a fifth group element like arsenic, antimony, phosphorus and bismuth is added, then it results in a N-type semiconductor. Here, every fifth group element has 5 valence electrons and the 4 are shared by 4 silicon atoms and there is one remaining valence electron. So, it can donate another electron to another atom. So, there is a vacancy of another electron. So, this type of fifth group elements or the pentavalent impurities are called as donor impurities. These are called as the donor type impurities. The fifth group impurities are also called as the donor type impurities. So, we can represent this like this. Here the conduction band, valence band, and there exists a donor energy band for this N-type semiconductors. So, the energy gap of donor energy band is smaller than conduction band and valence band, which is very small, and its value is about 0.01 electron volts per germanium. That means this is 0.01 electron volts per germanium and 0.05 electron volts for silicon, which is very less when compared to conduction EC and EV. The impurity is having one extra electron and is presented in the donor energy band. That is, the extra electron is present here. First donor electron moves from donor energy gap to the conduction band because the energy gap is less between donor energy band and conduction band. If the free extra electron moves from donor energy gap to the conduction band, there is no way to form holes in the donor energy gap because the extra electron does not participate in bonding. Example, that means the N is approximately equal to capital N into capital ND. The number of electrons, that means the number of electrons in conduction band, the number of electrons in conduction band is approximately equal to the concentration of electrons in donor energy gap. Donor energy gap, that is ED. Okay. So, here the number of electrons are equal to the number of electrons in donor energy gap. So, this N-type semiconductor looks like this. Here positive sign is due to because it is donating the electrons. So, it acquires the positive charge, and here the majority charge carriers are the electrons. So, there are more number of electrons in this structure and there are less number of holes. So, the minority carriers of N-type semiconductors are holes, smaller amount. That means the minority carriers are the holes. This can also be written as, we can write it as like this. We can represent a N-type semiconductor like this also. Here in an N-type semiconductor, the number of electrons are the majority charge carriers and the holes are the minority charge carriers. Similar is the case for P-type semiconductor, but in an opposite way. Here N is far greater than P. That is, the concentration of electrons is more than the concentration of holes at room temperature. At high temperatures, if the temperature is more, then the extrinsic semiconductor will behave like a intrinsic semiconductor. That means N is equal to P. When the number of electrons is equal to the number of holes, then it becomes an intrinsic semiconductors at high temperatures. So the total current I is equal to In of II plus In of BB plus IP of BB. This is the current due to electrons and this is the current due to holes, and In is far greater than IP in N-type semiconductors, where In of II is the current due to impure ionization, and BB means it is due to band to band transition, that is current due to band to band transition. So the total current I is equal to sum of the current due to electrons and current due to holes. Now let us go to P-type semiconductors. So what is meant by P-type semiconductor? If an intrinsic semiconductor is added with the third group elements, that means third group impurities such as boron, gallium, indium are called as P-type semiconductors. When intrinsic semiconductor is mixed up with the impurities like boron, gallium and indium, it results in a P-type semiconductor. In third group elements, there are 3 vacancy electrons. That means there are 3 valency electrons in their outermost shell. So boron has 3 valency electrons. Here there is a need for one more electron. That means this is called as an acceptor type. These impurities are called as acceptor type impurities. The 3 electrons are shared by 3 silicon atoms and the 4th silicon atom requires another electron. So it is a acceptor type impurities or trivalent impurities. The energy band diagram of P-type semiconductor is as shown like this. Here this is the conduction band, valence band, and this is the acceptor energy band. That means here the valency electron from valence band moves to the acceptor band, as the distance between the valence band and the acceptor energy band is less, very less when compared to conduction band. While the electron moves from valence band to the conduction band, the acceptor energy band accepts the electrons and becomes negative charge, and holes created in valence band Due to the movement of electron, there is a hole created in the valence band. As the temperature increases further, these created electrons in EA moves to conduction band. If the temperature is increased more, then the electrons in the acceptor energy band move to the conduction band. So the P-type semiconductor can be represented like this. The negative sign for the ion, because it is accepting the electrons from other atoms. So it can be represented as negative sign. And the majority carriers here are the holes. So they are represented in large number. And the minority carriers are the electrons. So it is represented in a less number. Here the carriers P are more when compared to electrons. So P is far greater than N here. And similarly, the current due to holes is more when compared to current due to electrons, and this also be represented as like this or with positive charge. So the total current I is equal to IP of II plus IP of BB plus IN of BB. That is the current due to holes and current due to electrons. The total current is the sum of current due to holes and current due to electrons, but the current due to holes is more when compared to current due to electrons. This is due to impure ionization, and this is due to band transition of holes and electrons. So we can say that in semiconductors there are two types. One is the intrinsic semiconductor and the other one is the extrinsic semiconductors. And the intrinsic semiconductors are formed due to pure semiconductors, and the extrinsic semiconductors are formed when the intrinsic semiconductors are added with impurities like fifth and third groups. If fifth group impurities are added, then it is an N-type semiconductor. If third group impurities are added, then it is a P-type semiconductors. So the P-type semiconductor is an acceptor type semiconductor and the N-type semiconductor is a donor type semiconductor. So up to now this is clear to you. Let us discuss about the P-type semiconductors and N-type semiconductors in detail in our next session. So thank you for watching my video. If you like my video, please do like, share and subscribe to my channel. Thank you. For any doubts and comments, please do comment in my comment box. Thank you.